Good morning, everyone. We'll be starting in 1 to 2 minutes time. Good morning, everyone, and the lectures that we're going to be doing today are going to be focused on the fast Fourier transform and how this technique can be manually applied using what we refer to as the butterfly diagram approach in order to solve for transforming the discrete time signal into its discrete frequency representation. In particular, we saw in our last lecture where we transformed the DTFT, meaning the discrete time Fourier transform, into the discrete Fourier transform, the DFT, and how the DFT actually can be applied to our discrete time signals to get their discrete frequency representations. But we also saw that the DFT, when we started analyzing its computations, that it did too much calculations in particular once we started expanding and going up in terms of the number of samples. So the DFT didn't scale well as n increased, so to say. So what we also observed is that there were ways for us to speed up the DFT, but the FFT is more like a improved speed up version of the DFT, and that's the algorithm or technique that we're going to be using throughout the course for changing a discrete time signal into a discrete frequency signal, so forth. Alright, so let's get started. In reviewing what we did in Monday's lecture, we saw that in using the DFT, we had something referred to as 12 factors here. And these 12 factors had a symmetry property and a periodicity property that we could have took advantage of to reduce the number of calculations required in order to obtain our discrete frequency representation. One thing we can also note in order to speed it up even faster is that if the number of samples being capital N is a power of 2, we can actually split that DFT sequence into 2 separate sequences, where it'll be odd index sequences and an even index sequence. So if we had a sequence of 8 numbers and the indexes was going 0, 1, 2, 3, 4, 5, representing each one of the values, splitting it, we'll only take all the even index numbers here and then the odd index numbers here, and we'll perform the split here and then perform the DFT on each one of these accordingly. So mathematically, what this means is, instead of having our full DFT equation here represented by xn of k, we now split it such that we have x of nk going such as it uses 2r here, where this represents our even sequence, and the 2r plus 1 here represents our odd sequence. And the combination of the two when you add it back up will give us back x of nk accordingly. Now, in doing that split, it also means that we can keep on continuing this same method for splitting the indices as we keep on going. Because we start off here where we split here into even and odd indexes, then we can just take these indexes here and say, okay, every even index here, be it 0, 4, 8, 12, we can split that again, and all odd indexes in this sequence here will be 0, 4, 2, 6, 10, 14, and we can split it here accordingly, and we can keep on repeating these splits throughout the entire thing until we get down to like 16 signals of 1 point each. And in doing all these splits here, this allows us to speed up the DFT dramatically, because instead of having all these number of points here to do the DFT calculations, we now just only have to do the DFT calculations for only one set of points in particular, and that's a lot faster to do than having to include all the additions that were also computationally expensive. So we started off with a 1 signal by 16 point, then we go 2 signals by 8 points, 4 signals by 4 points, 8 signals by 2 points, and then 16 signals by 1 point. And in doing all these splits here, we're going to observe in the next few slides how this actually speeds up the DFT. In doing all these splits here, this is actually how we start approaching what we refer to as the fast Fourier transform, or the FFT, which is an optimized version of the DFT here. So, and watching the first split of the DFT equation that we just now saw in the previous slides, and we had the 2R sequence here represented our even index sequence, and the 2R plus 1 here represented our odd index sequence. Once we have a lot more identical terms, because of these splits, that means we don't have to keep on computing new items. We can just reuse those values in particular. And that also allows us to speed up the DFT, because we also further reduce the number of calculations required. So, in watching that equation here where we had W of n 2R plus 1k, it's possible for us to split this into W of k 2R and then just WK here, because this is just an index power here that we can just split accordingly. And in doing so, that means we can rewrite our equation now, such that we'll have W of n2 R of k here and W of n2 R of k here as well. And we just need to factor out this WK of n here only for the odd index sequence. Now these two factors here are the same. So that means that what we calculate for one, we're basically calculating for the next set here, for the odd and even index sequences. And we also know that from the symmetric property of the total factors here, we can also split this accordingly. So we can just speed up this calculation even further by using that symmetry property. Because we saw basically, in doing so, once we had that symmetric property, it becomes easier for us to map the 12 factors accordingly. And we saw that in Monday's lecture. So in splitting that and rewriting the equation here to even make it more optimized, we obtain the fast Fourier transform, or the FFT equation, for that DFT equation that we started with. Now, note one thing here, because we had started with an n sequence here, and the summation series now are now going to be half of that sequence being n divided by 2. And the summation sequences here, remember, because of the split, these are now going to be 2n divided by 2 points, where these are going to be DFT equations. And if we analyze the time savings for these, we see here that instead of having all those massive computations that we just now had regarding when we just did the DFT straight, we have a good time saving factor accordingly for doing the FFT here. So we see here for 8 point, instead of having 64 calculations, if we did for the DFT in particular, we now only have 36 calculations to watch out for. So we save a factor of 28 multiplications. And then if we keep on scaling it up, we see that we have a huge saving of the amount of calculations that we did to begin with. In comparison, like 1 million here, we know when you have like approximately about half of that. And when you watch it in time as well, we have a huge time saving as well in using the FFT instead of using the DFT. So those splits that we saw when we split the DFT, they're also referred to as decimations in time. There's also a decimation and frequency method, but we typically don't really use the decimation and frequency method because we're more focusing on using the discrete time signals to obtain the discrete frequency representation. So when doing those decimations in time, in particular, instead of going all the way down to 16 points by 16 signals by 1 point, we only keep on going until we have 2-point DFTs. And once we have those 2-point DFTs, we then formulate that back in order to form the FFT equations in particular. And using the 2-point DFT, the name for this algorithm is known as the radix 2 FFT, because we go straight down to only 2 points accordingly. And we're also dealing with sequences that are a power of 2 in particular. So like I said, remember, this algorithm works only when the elements in x of n is going to be a power of 2. So it's going to be like 2, 4, 8, 16, 32, and so forth. In instances when you don't have a sequence that's a power of 2, but you do want to use the radix 2 FFT, and we want to observe this in the next few lecture, the next lecture, is it's possible for us to like to add zeros to the end of the signal, so that's called like zero padding. So until we reach the next available power of 2, and then we can perform the FFT as well. But we want to observe that in the next lecture as what's going to be the effect of zero padding in the signal and how it affects the frequency components in particular. So let's watch a 4-point FFT example here. And we're going to see how we can formulate our FFT here visually instead of using this summation series mathematically. So if we split this 4-point FFT here into the odd and even sequences, so the even sequences here being 2r and the odd sequence here being 2r plus 1, and we rewrite our equation here into the optimized form that we just now did all the mathematical proof for, let's actually start expanding this and see if we can observe any patterns in particular. So if we calculate first such that we have our x of 0 of x of 2, and then we have our x of 1 and x of 3 here for all our total factors as we keep on going. So this is for x4 of k here, where we had this value here in particular. Let's actually start going in for k equals 0, 1, 2, and 3 for us to get our frequency components. So x4 of 0 here, well, we substitute this in and we have our total factors substituted the value of k here. If we visually draw this out, we see here we have x0 and x2 here. So we can put this on the left hand side representing our inputs. And in formulating the equation, x0 goes towards the summation point, so that's going to be the x1 plus here. And x2 multiplies by w4 of 0 here and adds to x0, so it goes to this summation point as well. We can then put x1 and x3 here, because like I say, the left hand side is going to be our inputs visually. And we can also see that calculations here also take the same pattern. x1 goes plus, and then x3 multiplies by w4 naught, and it goes to that plus as well. And then the result of those two, where we just only have w4 here multiplying by x1 plus x3 w4 naught, they just go towards adding together to form x4 of naught here, gives us our answer. So keep in mind this visual representation for x4 naught, because we're going to be using this visual representation for the other frequency factor. So remember, this is only 1/4 because we now have to calculate for x41, x42, and x43. So let's watch for when it's x41, and let's see how the diagram itself changes. So we now have x0, x2, w4 of 2 here. So instead of putting them up, we're going to put them down in particular, because if you watch our previous diagram, these were going up. So we're going to be a little bit more symmetric, and we're going to be these go down instead. And similarly here for the x1 and x3, it follows the same pattern as well. And then we can see here that the last part is just to add W4 of 1 multiplied by the result of this x1 plus x3 here, with the result of the x0 and x2 here in particular. And we can formulate this. And we can keep on going and drawing our diagrams. And we can start seeing that a pattern here starts to emerge. Now, in this particular case, we have W4 of 4 here. And we represent this as W0 of 4. And if you can't remember why we represent it as a W0 of 4, this has to do with the periodicity property of the total factors. Because once you start going up in indices, so remember the total factors that exist from 0, 4, W to 0, 4, 3. And then it repeats afterwards because it's cyclic and it has a period of 2 pi. So once you hit W4, 4, that comes like, okay, you made the full revolution here, which is 2 pi, so you're not going to be starting back at W4, 0. So that's the periodicity property of the total factors here. So we can keep on mapping these out accordingly. This here is supposed to be so let's say it needs to fix on the slide. This is to be x42. That's to be 1, that's supposed to be 2 here. This one here is supposed to be 3. And we can keep on drawing these out for each one of the quarters, being the frequency couplets that we're trying to calculate for. And we can see basically some sort of pattern emerges if we start observing each one of these in particular. So watch here for like the x0 for 1, we see that we have a W24 here, W24 here, and the direction of the arrows give us an indicator of how the calculations go. And then if we watch here for x43, we have that same W204 here, W204 here. The only difference is the W43 here for our calculations. So when we all show these in particular, we see that we have some sort of pattern that emerges from when we combine all these calculations together. And we can observe this pattern visually. This is what we refer to as our butterfly diagrams, because you can see here, the butterfly is going by this center point, and this first triangle here is going to be a wing, and then this triangle here is going to be the wing in particular. Similarly, if we watch this center point, this is going to be the wing of the butterfly here, and this here is going to be the next wing of the butterfly here. So this is how it got the name, the butterfly diagram in particular, by observing the patterns visually here and doing these calculations. And observing these patterns and seeing how we can actually speed up the FFT visually by these patterns, it becomes possible to actually perform the FFT using these butterfly diagrams. And we'll actually do a worked example in order to observe this. So if you watch the butterfly calculation step by step here, we can see that in just using the x0 and x2 values from our discrete time signal, it's possible for us to only formulate our x4 of 0 and our x4 of 2 values here in the discrete frequency domain. And then similarly, if we watch the x1 and x3 values here, and we watch the direction of the arrows that they're going to be in, it becomes possible that using the x1 and x3 values here, we can formulate the x4 of 0 and x4 of 2 values here in the discrete frequency domain. So if we actually perform the calculations here, you can see here that for each one of these 12 factors, and we saw the 12 factor equation in Monday's lecture, we can calculate out the 12 factors here, and then we can just perform the series of calculations here to get our discrete frequency representation of the discrete time signal that we started with. So the algorithm that we're going to be using throughout this course for the FFT is going to be the radix 2 algorithm, but programmatically there are more algorithms that do exist, and some that are way more efficient than the radix 2. And the radix 2 is possibly the most simplest one you can actually learn and actually visually observe as to how it operates. So for this course, we'll be using only the radix 2 Fft algorithm. And visually, that means we're going to be using the butterfly diagrams in order to calculate our FFTs. When you actually start dealing with any DSP chips in particular, there are specialized chips that have even faster FFT algorithms, which can be programmed and reprogrammed. Even if you don't want that algorithm and you find a more improved algorithm, you can just program it in straight. Because these specialized FFT chips are programmable, it's also possible for you to do any further operations on the signal itself. And to give you an idea of how fast these can actually perform, if you have a 1024 point FFT and your modern DSP can now go well under 5 milliseconds to calculate this in particular. So let's watch a practical example here, if we try to find the DFT of this signal. And first question we're going to ask, okay, what's going to be our output frequencies? So in having this x of n signal here, we know the output frequencies when we actually did the DFT or the FFT. We're going to have 8 frequency components. That's going to be from x0 here to x7. And in applying this in the DFT equation, which was our fancy summation series here, and watching the signal, because x5, x6, and x7 here for x of n at 0, that means we don't need to calculate the DFT for these points in particular. We can reduce the summation series here for k equals 0 to 7. We also know that this being an 8-point DFT, that means we're going to have total factors going up to 8. So we draw our phasor diagram representation and then calculate each one of these total factors here in particular. Hopefully you guys tried doing the total factors for 8 and 16 in Monday's lecture, so that you can actually observe the patterns that emerge when you start scaling up the total factors or when you start scaling them down. And then if you wish to calculate the total factors using MATLAB or Octave, this is the command that you'll be using in particular. Remember, this is for an 8-point total factor. That's why we have 0 to 8 here. And we're dividing by 8. If you are going for a 4-point, this 8 here will just change to 4. If you're going for a 16, these 8 here will just change to 16 and so forth. So this actually will give us a nice vector here for all our total factors and do all the calculations for you immediately. We can see here from the symmetric property of the total factors, there's no need to actually calculate all the 8 values, because we see that W0 of n here being 1 is just going to be minus that for W4 of n in particular. And same thing for W n1, and that's going to be minus Wn5 in particular, and so forth. And then, because we have these total factors here, we can just calculate from x0 to x7 here for frequency components. So if we were doing the DFT and we did the long version, and we have our total factors here in particular, and we start summing in particular, we'll see we get x0, x1, and we can just complete all the rest, and we can see that it's going such and so forth and so forth, until we actually obtain our values. But in doing so, remember, when we did the DFT here, this means that we want to be calculating for 8 by 8, so we're going to have to be calculating for 64 total factors because of that k index that's going to be factored in here, because it was W and k of n here, and that's not going to be very effective. So in the next lecture that we're going to do, we're going to see how we actually apply the FFT here and how it's going to be a lot more simpler to actually perform, to actually obtain the discrete frequency representation of that same x of n signal that we started with. So the same x of n signal here, in the next lecture that we're about to do, we're going to see how we actually perform the FFT here instead of doing all these complex calculations that's required, and how simple it's going to be to just calculate it in particular. Alright, so that brings us to the end of our first lecture. Are there any particular questions? we're actually on slide 23. Back. So this command here will give you all the values listed. But instead of having to calculate all the 12 factors, remember, because of the symmetric property, W naught of n here is just going to be minus W4 of n here. Similarly, W1 of n here is just going to be minus W5 of n. So if you watch this value here, we basically see that 0.7071 minus that same value imaginary. This comes like we just multiply this entire thing by -1, and we see here this value here becomes negative, this value here becomes positive, and so forth. And that's because of the symmetric property of the total factors. So yes, the values obtained are due to the symmetric property. X naught here, when we calculate it out, remember this here in the discrete frequency domain, the 0 component is the DC component. So that's how you end up getting only a real value here of 15. So when we actually calculate this out, and the total factors, you actually see here that you're going to only get real values, you're not going to get imaginary values whatsoever. And this is because X naught is the DC frequency component. Anything else than X naught is going to be AC frequency component, so like the first sideband, the second sideband, and so forth. So that's why you're going to get imaginary values for these in particular. Reason for this being is that because of that symmetric property that you just observed in the previous slide, watch this value here in particular, which is minus 0.7071i. This imaginary value here is going to cancel this imaginary value here. Similarly, this imaginary value here being minus 1i, cancel with plus 1i here, and so forth. So you're only going to be left the real value components here when you're doing that calculation for X naught. Alright, doesn't seem like we have any further questions at this point, so let's move on to the second lecture. Give me 1 second, guys. Alright, so for this lecture in particular, we're going to be using the Fft approach instead of the Dft. Reason for this being is that if we did that Dft approach that we also saw in the last slide, in doing that Dft approach, remember there's a lot of calculations involved, and we're trying to figure out a more optimization of the Dft. It's going to be our Fft approach here. So this lecture here is going to focus on how we actually apply and use that Fft to obtain our frequency domain representation. And we want to see in that using the optimized Fft, we basically approach to the same answer if we're doing the long version of the Dft instead. So we're going to be using the same x of n sequence here, and we're going to be using the Fft version instead in order to solve for it. Now, it's going to be similar to that when we were doing the Dft equations, but remember the Fft here is just going to decimate that Dft in order to speed it up. So that means we know we're going to split this into the even index and the odd index subsequences here in order to start this. And in doing so, that means we split the Dft equation here into this form. And this is going to be our even index sequences because of that 2n here. So that's mean the inputs here is going to be x0, x2, x1, xx. And this part here is going to be our odd index sequences, where the inputs are going to be x1, x3, x5, and x7. So if we did the Dft manually, remember, we'd have all these long calculations here in particular, and this tends to be really long and complicated to do. And doing the split here, we see now that the calculations become a lot easier to do. So remember, we will represent each one of these inputs here now and the outputs here by x for the inputs, yes. But the outputs here are going to be E0, E1, E2, and E3 because we represent this as even index sequences. And the outputs here are going to be O0, O1, O2, and O3 here for the odd index sequences in particular. So if we map those split here back into terms of even and odds, the equations here become a lot easier to write and a lot easier to represent. So in doing so, we are able to get all our frequency components by just using this notation here in particular. And it's a lot easier to do these calculations as we're going to see in the next few slides. So let's examine the behavior of x4 in particular. Remember that we have W4 of 8 here, but it's possible to represent this using half of the total factors here by using the symmetric property. So that means that for everything that was W4, W5, W6, we can now map this back to W0, W1, W3, but it's going to be the negative counterparts instead. So we can rewrite this entire equation that we had from x0 to x7 here in terms of just W8 all the way up to W83. And we see here basically that the difference is just the signs change accordingly. So instead of the first half being plus, the second half here is just going to be negatives for the sign change. And when we map this into the butterfly diagram, and we start actually doing this in particular, we see here that for each one of these, it's going to be the same butterfly, just it's going to transpose for 0, 1, 2, and 3 in particular. And the same thing for the 12 factors, W8 0, W8 1, W8 2, W8 3 in particular as well. So after doing all those 12 factors that we superimpose it, you'll see that we get this nice fancy butterfly diagram, which actually gives us a nice visual representation for how we actually can do this. And don't worry, we're actually going to apply it to that starting signal in a little bit, step by step, so you can actually get a full understanding of how it's being applied. But for now, we're using symbology here just to show how the butterfly diagrams keeps on breaking up to simplify the calculations for us. So this is also another approach to the butterfly diagram, which we will we're going to observe and which we want to be using in particular. So let's examine what happens when, instead of after the first decimation that we just now saw, we're going to decimate one more. So we're going to decimate these into 2-point DFTs from that 4-point DFT that we did from the first decimation. And we can formulate our equations here and so forth. And what this means here is that for those 4 points, excuse me again. Sorry about that. So for those 4 points that we just now had from that first decimation stage, we now split this into 2-point DFTs. So we're going to be using the even indexes from those 4 points here, and the odd indexes from those 4 points in particular as well. So the symbology here makes it that it's a little bit confusing to track, because that means now we're going to be using 2-point FFTs here, the even index even subsequence, as well as the odd index even subsequence. And yes, I know the terminology looks very weird, but it's going to make a lot more sense when we actually apply it to the numerical sequence. So just bear with me a little bit until we actually reach the numerical sequence and we can actually observe how it works. So what that means here, instead of having W of 8, we know when you have to calculate for W of 4 because of that decimation. So this reduces the amount of total factors we need to calculate for in total. The similar thing happens with the other 4-point sequence that we had, which was basically the odd index sequence. That means now we're going to be taking the even indexes of that odd sequence and the odd indexes of the even sequence as well. And we do the same thing as before. Same thing with the total factors here. Instead of having 8 total factors to calculate, we now only have 4. And because it's a metric property, that means we only have to calculate for 2 as well. So it keeps on speeding up as we go with the decimation stages. So after that particular decimation stage, we see here that our butterfly diagram here modifies a little bit. Instead of having all the 12 factors here on the bottom, we now have the 12 factors represented in pairs instead. And we can keep on going until we decimate into a set of 1-point DFTs and so forth. And we can see here at this point, the 12 factors are just going to be 0, 2, 0, and 0, 2, 1. So that means for every 2 values here, there's going to be no total factor, a 12 factor, no total factor, 12 factor, and so forth. Because no is just because it's 0, 2, 0, and 0, 2, 1. That's just going to be at the positive 1 line and the negative 1 line on our 12 factors accordingly. 0 degrees and 180. So in substituting for the 12 factors here calculated before, and we're actually going to be compounding each one of these decimation stages that we just now saw, it makes doing the butterfly diagram analysis a lot easier, and instead of having to do that long DFT, it makes doing the FFT a lot easier as well. So if we actually did all the calculations here for the DFT, for x0, x1, and kept on going, we see here that in doing the DFT example, we get all our frequency components here for x0 to x7. We're going to be using this as a reference answer, but when we actually start applying the FFT here to our input sequence instead. So let's actually use the x of n sequence that we have here, and we're going to be applying it to the FFT sequence instead, and see how we can actually approach to this final answer here, given by x0 to x7. Now, recall here that our input sequence when we started was 1, 2, 3, 4, 5, 0, 0, 0. The starting sequence here, when we start doing this for the FFT, and I'm going to explain this on the last slide in particular, is where we need to make sure that these values here are organized in a particular order. So like I said, on the last slide of this lecture, I'll explain how do we obtain this order for the sequence here to start the FFT. once we have this calculation here in particular, sorry, this sequence in its particular order, we then perform the calculations here for the first decimation stage. So if we watch here, this 1 value here will just go straight across. This 5 value here will go across here, the diagonal. And we just add the 2, so we get 1 plus 5 here, which gives us 6. Similarly, this 1 value here will go across the diagonal. So that's going to be 1. This 5 value here is going to go across here, and it's going to be multiplied by -1. So that's going to be 1 minus 5, because 5 by -1 is obviously -5. So we get a value of -4. Similarly, for the other pairs here, there's going to be 3 plus 0, so let's get 3. Then 3 here, plus 0 by -1, so we get a value of 3. 2 here, plus 0, so that's 2. So because of the 0 here, that means we also get 2. Same thing for the 4 and 0 here, it's going to be 4 and 4. So this gives us the output of our first decimation stage. We then take the output of our first decimation stage here. I will put this in as the input of our second decimation stage. So apologies again, let me be right back. Let me make sure I get something to clear my throat. So apologies for this. Alright, hopefully I should be fine for the next half an hour. Just took a little bit of medication here. So my apologies guys, but I do have a little bit of an allergy problem with this iron dust. And it is affecting my throat a little bit, so bear with me a little bit. There may be times I might end up coughing uncontrollably, but like I said, it's basically an allergy problem at this point in time. I really can't do anything much about it. So let me continue the explanation here in particular. So when we completed our first decimation stage here and we obtained our output, it was possible for us to use the output of the first decimation stage and use this as the input towards our second decimation stage. In formulating the input of the second decimation stage here and doing the butterfly diagram here to get the output, we see here that if we consider only the parts that had 0, 0 or 4, the 6 value here will go straight across, the 3 value here will multiply by 0, 0 or 4, and a total factor here, anything that's 0, 0 or 4 in particular is just going to be 1. So we get 6 plus 3 here, which is going to give us 9. Similarly, this here being 6 will go across here. This is going to be 3 by 0, 0 or 4, and 0, 0 or 4 is just going to be a value of 1. So it's going to be multiplied by -1, so we get 6 minus 3 here, so we only get 3. The same method is observed here for 2 and 4. So 2 and 4 will add and give us 6, and 2 and 4 here will just minus to give us -2. When we move to the next parts, in particular we have W1 of 4. Remember, W1 of 4 here is going to be minus G. So when we calculate out for this value here, this is going to be 4 going across here. And this here is going to be 3 multiplied by W1 of 4, which is going to be minus J. So we're going to get minus 4 minus 3J here. Similarly, this minus 4 is going to go here. This here is still going to be minus 3J, but this is going to be multiplied by -1. So this becomes minus 4 plus 3J. And you can see here that we observe a pattern that emerges when we're doing our calculations. So for the next part here, this is going to be 2 plus 4, sorry, 2 and 4 here is going to be multiplied by W1 of 4, which is going to be minus J. So that's going to be 2 minus 4J. So the next half for this butterfly diagram is going to be 2 plus 4J accordingly. So in combining all the calculations here for the second decimation stage, we get the output of our second decimation stage here. But we can see here that the first, third, all our odd values here are going to be real components, and our even values here are going to have imaginary components in particular. We then take the output of the second decimation stage and we use it to formulate the output of our third decimation stage by treating as the inputs here. So when we do for the first part here, being the first pair of values, this here is going to be 9 and this here is going to be 6. W0 of 8 here is just going to be a 1, so it's going to be 9 plus 6 giving us a value of 15. And because we did the addition here, that means the next half is going to be a subtraction, so that's going to be 9 minus 6 giving us a value of 3. Similarly, for the next half, the next pair that we're doing, minus 4 minus 3J here will go across here. And 2 minus 4J here, when we go up with W1 of 8, remember, this here is going to be a complex quantity. And we saw that complex quantity when we actually did the evaluation for those 12 factors. So this is actually going to be minus 0.7071 minus 0.7071i, or j in this particular case. But we need to multiply this by that total factor, and then we're just be adding the two results. So we get our imaginary components here accordingly, which will be the addition of these two with the total factor. And then for the next half, there's going to be the subtraction of these two here with the total factor in particular because of this -1 component. And we can keep on going until we obtain our answer. And this answer that we obtain here is going to be our final answer. And keep in mind that this final answer is similar to that of the DFT answer that we had here. It's going to be the same answer. So this is actually how we actually perform the FFT to obtain our frequency domain representation, our discrete frequency domain representation of that discrete time signal that we just saw. Now, there are a few things to note in particular when we are setting up this butterfly diagram. And this also refers to as our first, second, and third decimation stages. So for the first decimation stage, when you're setting up the butterfly diagram, it's going to be no -1 here, then a -1, then no -1, a -1 here, and so forth. So for every two values, there's going to be no -1, but then the second value here is going to have a -1. And this is because if we say this being at the first decimation stage, 2 to the 1 is 2, that means we only focusing on every two values, also every pair of values. We have to figure out where do we put our -1 value here and our associated total factor as of such. But because of this first decimation, we don't have any total factors, so it just would be every two values. The first value here is going to have no -1, but the second value we must have a -1 and so forth. For the second decimation stage here, this is going to be 2 to the power 2, so that means we're going to be dealing with 4 values in particular. Remember, first decimation, because it's 2 to the 1, that means we're going to be dealing with 2 values. At the second decimation stage, that means we're going to be 2 to the power 2, which is 4 values. Because we deal with 4 values here in particular at a time, that means for the first half of these 4 values, there's going to be no total factors or no -1s involved. But for the second half of these 4 values, we're going to have a total factor and a -1 component. So I'm going to just jump to the final version. So remember, when setting up for the second decimation stage, because it's 2 to the power 2, which is going to be 2 to the power 2 here being the second decimation, which gives us 4 values we're going to be dealing with at a time. The first half of these 4 values are not going to have any total factors or -1s, but the second half of these 4 values will have total factors here and -1s. Note that the index here of the total factors is also going to represent this 2 to the power 2. That means it's going to be 0,4 for these here, and this one here is going to be 0,40 and 0,41 accordingly. Similarly, for the second half of the 8 values that we're dealing with, the same pattern is going to be observed for setting it up. So, because it's 2 to the power 2 and we're dealing with 4 values at a time, this means we're dealing with the next set of 4 values. So, the first half of these 4 values will have no total factors or no -1s involved, but the second half here will have total factors and -1s in particular. And because we have total factors here, that means we're going to have to make sure that it's W4 because of 2 to the power 2 here, representing the second decimation stage, sorry. And as of such, that means the index here is going to be W4, 0, and then W4, 1 here accordingly. And then finally, for the third decimation stage, this is going to be 2 to the 3 here, which is 8 values that we're going to be dealing with at a time. So the first half of those 8 values, there's going to be no total factors and no -1s. But for the second half of these 8 values here, there's going to be associated total factors and -1 components in particular. Because it's 2 to the power 3 here, representing the third decimation stage, that means the total factors here is going to have a base index here of 8. So that's why we have W of 8. And then for each one of these going down in term, the index here is going to be W80, W81, W82, and W83 accordingly. The reasons why we have these -1 values is to represent that symmetric property of the total factors. So this represents when we have W04 here and it multiplies by -1. So I'm writing this on the slide here to give you an idea what I mean. So W0 of 4 is basically equivalent to the of W. Oh, I'm writing this wrong side. My apologies. W4 of naught here, sorry, is equal to the same thing as negative W4 2. Similarly, W4 of 1 is the same as negative W4 of 3. So this comes like if we say these here are positive on the right hand side, that means these here need to be negative on the left hand side to match back the equations. And the reasons why we have these -1 components here in particular is to map such that we get back W4 of 2 and W4 of 3 here when we're doing our calculations. So that's why you have those -1s always associated with the total factors to map back to the other halves of the total factors in particular, because of that symmetric property. So the compound effect of all of these decimation stages here and doing the total factors and so forth in particular will give us our frequency domain representation of that discrete time signal. And this method that we use there is efficient in actually calculating the FFT of that signal. So before I move on, are there any particular questions that need to be addressed? Because like I said, this method that we observe here is what we're going to be using for performing the frequency domain, sorry, the FFT of any signal that you'll be dealing with in this course. So if there's anything you're unclear about, ask at this point. Let's make sure that you do understand anything that is giving you trouble or something that you're not clear about. Yes, the number of decimation stages is dependent on the number of elements in X of n. So remember, this algorithm that we're using here for the FFT is the radix 2 FFT. And the starting point for the radix 2 FFT is that the sequence must always be a power of 2. So let's say if we went up to 16 points, that means that's 2 to the 4, and that index 4 there represents the amount of decimation stages that you're going to be using. That means 16 points being 2 to the 4, that means you have 4 decimation stages. E represents the even indexes, and O represents the odd indexes for those sequences. Now we also get a lot more practice with doing the FFT when we actually start doing problem set 2, and I know like the slides here just basically give you kind of like an automated explanation, but when we actually start doing problem set 2, you'll get a full manual explanation as to how we go about formulating those butterfly diagrams, as well as how we do all the calculations and so forth. Like I said, when we start doing problem set 2, I'll be showing you guys step by step how you can actually use MATLAB in conjunction to do the total factor calculations, and how we actually can use it to actually formulate our FFT diagrams in particular as well. Any further questions in particular before I move on to I believe it's the last slide for this lecture? Alright, doesn't look like we have any further questions. So, alright, let's move on. So, in setting up the input sequence here, but when we start doing our FFT, remember we'll have common x of 0 going away to common x of 7. And we need to make sure that we get to this sequence here before we actually start performing the FFT with its first decimation and so forth as we keep on going. And I was saying that this last slide here explains how do we make our x0 to x7 discrete time signal into the starting sequence required for the FFT. So what happens here is that we need to convert these indexes here, being 0, 1, 2, 3, 4, 5, 6, 7, into its binary representation. Once we have it in the binary representation here, so remember 0 is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, and so forth. We then swap the first bit and the last bit of these binary numbers. So instead of having 0, 0, 1 here, because we swapped the first and last bit, there's now going to be 1, 0, 0. This one here is going to remain the same because we had 2 zeros on the ends. This one here is going to be 0 and 1 is going to swap, so let's go 1, 1, 0, and so forth as we keep on going. Once we do this swap here for the first and last bits of the binary representations, we just convert these back into its decimal representation. So 0, 0, 0 here will give us x0, 1, 0, 0 here because this is binary, and we do binary to decimal. This will give us x4, this one here is x2, this one here 1, 1, 0 gives us x6, x1, x5, x3, and x7 accordingly. And this is actually how we get our starting sequence here for the FFT. The sequence, this process, sorry, is also known as the bit reversal process. So before you actually start doing the FFT on any discrete time signal, you need to do the bit reversal process to get the starting sequence for the FFT algorithm. Once you actually do this bit reversal process and you have the starting sequence, then you can start doing the FFT accordingly. Alright, so any particular questions on the material here or on the bit reversal process at this point in time, because we've reached the end of the second lecture? This x4 here? No, that's supposed to be x4. This one is supposed to be x1. That's correct. Remember, we did the bit reversal process. So we swapped the first and last bits here. So x1, it's in its binary form, is 0, 0, 1. And then when we swap this, this 1 here will go to the left hand, the 0 will go to the right hand, so we get 1, 0, 0. Oh, okay, alright, I understand what you're talking about. Right, so The bit reversal process here, remember the indexes here go from 0 to 7. So we just convert the indexes here into its binary representation. And then we do the bit reversal process by swapping the first and last bits. So 001 here, because we swap the first and last bits, that means the 1 goes on the left hand side, the 0 here goes on the right hand side, so that's called 100. Alright, nice. And then because this is 100 here, when we convert it back into decimal, that gives us 4 for the index. So that's how we get the bit reversal process here for the starting sequence for the FFT. Alright, nice. Okay, so doesn't look like we have any other sort of questions in particular regarding this. So like I said, when we do problem set 2 in particular, you will get a lot more practice doing the FFT here, and it'll be a lot more manual than what we saw on the slide, so you actually can see step by step how we actually formulate the butterfly diagrams and how we actually do each one of these processes in turn. And it'll be like I said, it'll be a lot more better for the explanations when you start seeing the process manually instead of on the slides here, which is a little bit automatic. Alright, so that brings us to the end of the second lecture for today, and what we're going to be moving on to is the select questions from set 1 that you guys voted on online. Okay, here, keep those annotation, that. Alright, so let me bring up the questions to be done here. Pull this one side. Alright, so only a few people voted, and from the responses here, we see that I did promise you guys I'll do 3 questions in particular. So question 7, question 5, and question 4 got the highest responses. So I'll do 4, 5, and 7 in particular. Question 3, if we got some time, I'll go into that as well, depending on how much time we have remaining. So I'm going to start with question 4 here, and I'm going to do this on my virtual whiteboard, so you guys can actually see how we go about doing this in particular. So question 4 here was talking about the continuous time convolution, but now we're going to be sampling it using 5 samples per signal and performing the convolution in particular. So we have the h of t signal here and the x of t signal, and we're just going to be watching these in particular. If we need to take 5 samples, let's take these 5 samples here from -1 to +2. So that's 1, 2, 3, 4. We're going to need 1 more sample. So the question asks for at least 5 samples per signal. So let's take it from -1 to +3. So we have 1, 2, 3, 4, 5. Right, that should be fine. 1, 2, 3, 5. Right, that's good. So in taking these samples here, and I want to need my whiteboard. Show you guys this. Bring this up. Anything here? Yes, I did. Give me 1 second. Okay, nice, good. All right, so let's put this accordingly. Whiteboard here. So we're going to watch our h of t signal here, and we're going to convert this into h of n. So h of n here, when we take our samples, and we're taking our samples from -1 to +3 from the x-axis. H of t here at -1, we can see that's at a value of 0. Then for 0, 1, and 2 here, this is going to be values of 1. That's 1, 1. And then for 3 here, that's going to be a value of 0. That's going to be 0 here. And then x of n We also be taking those 5 samples from -1 to +3. So -1 here, it's 0. That's going to be 0. 0 here is still 0. So that's going to be 0. 1 here is going to be at a value of 1. So we put 1. And then for 2 and 3 here, that's a value of 0. So we put 0, 0. So let's see if I still need anything here. Alright, so I just need to actually perform the convolution here on those sequences at this point. So we have h of n here and x of n. So in performing the sequences here, obtaining our discrete time sequences here, it's not possible for us to actually to perform the convolution using the convolution table. So I'm going to drop my table here, and I'm going to label my h of n sequence on top here, and my x of n sequence here on the left hand side. So our h of n sequence here was 0, 1, 1, 1, 0, and our x of n sequence here was 0, 0, 1, 0, 0. So I'm just going to draw in my table here. And then I'm going to be filling in the cells here for each one of these calculations. So 0 by 0 here will just give us 0. And then as we keep on going, that's 0 by 0. 1 by 0 is 0. This entire column here becomes 0. The entire row here being 0 by 1, 0 by 1. So 0 by 1 here, 0 by 1, 0 by 1, 0. That's just going to be zeros as well. So this here is going to be 0, 0, 0, 0. This here is also going to be zeros. This one here, which is 1 by 0 is 0, 1 by 1 is 1, 1 by 1 here is 1, 1 by 1 here is 1, so forth. 1, 1, 1, 0. This here is going to be 0, 0, 0, 0, 0, 0. So we have our convolution table here with all our calculated values. The next step is actually to sum across the anti-diagonals. Now, before I start doing that in particular, I want to know how many values are going to be required for us to get our y of n single. Because a y of n here, basically, if we take x of n and we convoluted it here with h of n. So L of x here had 5 values, and L of h here also had 5 values. So we know here that L of y is going to be L of x plus L of h minus 1, where L represents the length of the sequences. So L of y here is going to be 5 plus 5, sorry, minus 1, which gives us 9. So that means that we're going to have 9 values for the output convolution y of n here, which is a result of x of n convoluted with h of n. In formulating the anti-diagonals here, when I draw it on the diagram, you can see here that we're going to be watching it such that this is the first anti-diagonal. This here is going to be our second anti-diagonal. This here is going to be our third anti-diagonal. This here is going to be our fourth anti-diagonal. This here is going to be our fifth anti-diagonal, and so forth. So I'm going to do this here for the first 5, and then I'm going to show you step by step how we do it for the next 4. So let's see if I can backtrack a little bit. So for our first anti-diagonal here, that's just 0, so we're going to put 0. For our second anti-diagonal, that's just going to be 0 plus 0 here, so that's also going to be 0. Our third anti-diagonal, this is also only zeros here, so we got 0. Our fourth anti-diagonal here, we have 0, 1, 0, 0. We add those, that's 0 plus 1 plus 0 plus 0, so we get a value of 1. Our fifth anti-diagonal, 0, 0, 1, 0, 0. That's going to be just only a result of 1 here as well. Our sixth anti-diagonal, that's 0, 0, 1, 0. So we get a value of 1 when we add those. The 7th here is going to be just zeros. The 8th here is just 0 as well. And our 9th here, just 0 as well. And that's how we actually perform the convolution here for this question 4. Any particular questions? You can also see here that the lengths also match up when I did the calculations. Being Lx5, LH here is 5, represented the length of x of n and h of n. Calculation here for L of y was such that we have 9 values, and we count these values here 1, 2, 3, 4, 5, 6, 7, 8, 9, which matches up to the length that we calculated for. Any particular questions for question 4? Yeah, sure. So remember, we started here with our h of t and our x of t continuous time signals. No, we don't need to draw y of n. So the h of t and the x of t signals there are continuous time, and the question asks us to take perform the convolution in the discrete time domain, and as of such, we need to sample these signals accordingly. So we take 5 samples here from -1 to +3. So -1, 0, 1, 2, 3. So that's how we actually formulate those accordingly for h of n and x of n. Then we put the h of n on top and x of n on the left. It doesn't matter if we did put the h of n on the left and x of n, because the convolution can be performed in any order. You'll get the same output. So in doing so, once we formulate the convolution table here, we make sure each one of these cells are filled by a multiplication of the intersections as of such. So 0 by 0 will give us 0, 0 by 1 here will give us 0, and so forth. The next step is to make sure that we need to figure out how many samples are going to be in our output here for y of n. So we use this formula here, which is L of y is equal to L of x plus L of h minus 1, where the L's here represent the length of the sequences. So h has 5 samples and x here has 5 samples, and we just plug those in. So that's 5 and 5 minus 1. So we know y here must have 9 samples in particular. In formulating the anti-diagonals, which is probably the basis of your question here, we watch this such that we go along the table here to formulate our anti-diagonals. So I'll backtrack a little bit to give you an idea how we actually do this. So we watch, I'm going to highlight these in green, we watch these points here on the table in particular. And extrapolate this a little bit. So we watch these points on the leftmost column here of the table, and on the bottom row of the table as well, to figure out where do we start our anti-diagonals. And each anti-diagonal must go through any crosshair on the table. So when we did our anti-diagonal here for the first point, because this point here we don't really bother with, so don't start here. Instead, you'll be start here instead. So we watch these in particular. So like for this one, and let me just change this to blue here to give you an idea. And drawing this, that means we start here. So we want to be starting here in particular, but we need to go to the next cross point on the table. So that's why we get to watch diagonally what's going to be the next cross point and formulating the anti-diagonals. So we start at this cross point here on the table, and we go to the next diagonal cross point. Similarly, when we do this for the next anti-diagonal, we start at this cross point here, we go to the next diagonally cross point. So that means we'll be going here. And then from here, we go to the next diagonal cross point, which is going to be here. And we keep on doing those in particular for each one of these anti-diagonals in order to formulate them and then to just to sum the values across the anti-diagonals. So for this one in particular, which was the second value here, that's just going to be 0 plus 0, which will give us a value of 0. For the third anti-diagonal, that's 0 plus 0 plus 0, which will give us a value of 0 here. For the fourth, 0 plus 1 plus 0 plus 0, which gives us a value of 1. For the fifth one here, 0 plus 0 plus 1 plus 0 plus 0 gives us a value of 1, and so forth as we keep on going. So remember, in figuring out where the anti-diagonal starts, we just watch the leftmost column of the table here, and we watch the cross points in the table. And similarly, we watch the bottom row of the table to be, okay, this is where the anti-diagonals will also start as well. So hopefully that answers your question. So just reiterating for the other questions that were in the chat, no, we do not need to draw out y of n. Once you have the y of n sequence, that's the end of this question. And if the h of n would be placed on the left hand side and the x of n was placed on top of the table, you'll get the same output because the order of the convolution does not matter. Oh, if you're asking about where the y of n in x would start, it will not start at -1, but for our purposes, we don't really care for what the index is going to be for y of n in this particular case. We only care about what is going to be the values of the sequence. We don't care about start points for the convolution here in particular. If I did have to give you an idea of where it does start, however, yes, it will start at -1. Yes, it will start at that point. Right. Okay, so the next question we're going to be moving on to, because it doesn't look like we have any further questions regarding this question in particular, was question 5, I believe. Check this back. Yeah, question 5. So this here was, I'm just going to index this here on my whiteboard. Cool. Right, let's go to the next part here. So this is going to be 5. So question 5 here gives us an x of n sequence here. So we have an x of n sequence occurring at from n equals -5 to n 14. So let's visually drop this out. Sorry, let's visually draw this out. X of n here. Just draw a horizontal line representing this. This here is a -5 for start. And then n equals -5 and n equals 14. Put that in. And then x of n here for n -5 has a value of 3. And then for 14, we have a value of -4. So let's put this in as well. 3 and -14. And the question it asks what's going to be the index of the first non-zero value in the convolution y of n, x of n star, x of n. Okay. So I'm just going to watch this as a convolution in particular. So in doing the convolution, that means that we need to have this sequence here reversed for x of n. So that comes like if we have x minus n. So in reversing the sequence here, that means we'll have -14 and 5. And at -14, wait, hold on. I wrote something wrong here. -4, right. That's what I wrote wrong. Right. This is supposed to be -4, at -14 for the value. So in flipping this for convolution, that means instead of having +14 here and -5, that when reversing the entire signal, that means we're starting at -14 and +5. The magnitudes here do remain the same for the x of -n. And in observing where we have our start point now, we need to observe here that in doing the convolution, which is going to be x of n star x of n, this here, sorry, x of n here, that's our start. And this here is our finish. And in doing the convolution, because we have x of -n, this means that this here is going to be our start, and this here is going to be our finish. Reason for this being is that, remember, convolution would be if we had, I'm just drawing a rough sketch here, we had our x of n signal here. And I know this isn't what the signal actually looks like, but I'm just drawing an arbitrary indicator. And this here would be our x of -n signal, which also is like x of h minus n, or you could say n minus k in this particular case. However you want to represent it. This means that this point here will be intersecting with this point here. So that means this here maps to our start, and this here also maps to the start of x of n. That there is start of x of minus n. So in calculating for what's going to be our start here, because the question here asks for what is the index of the first non-zero value in the convolution, that means we just need to observe what's going to be our start points. So this here for x of n is -5, and for x of -n here, +5. And that means for this here being y of n, the index here is that if we watch at our start points, this means that we're starting at -5, but our reverse signal here, even though it starts at +5, remember when we transform this here into x of n minus k, we no longer care about whether this actually is going to be starting at +5 or -14, because this now transforms to a sliding signal because of convolution. So we're just going to use this 5 here as a reference, but we know here that we're going to be starting at -5 because x of n here is stationary. So this x of minus n signal here is going to be our sliding signal when we transform this into x of n minus k accordingly. So as of such, because we know here that the start point for x of n is -5, so x of n, which is stationary, is going to be at -5. This x of n minus k here is sliding. It's going to be at 5. And because we know the start point here is going to be at -5, that means we're going to have to factor in this -5 here being our start point entirely. So because this is a slide-in, that means that we only be focus on magnitude only. This part here. So starting index of y of n is going to be this -5 here, and we're going to move that -5 here. So we're going to move that minus side onto the outside because we're going to be focusing on the magnitude, plus 5. So our start point here is going to be at -10. So we need to factor in back this minus part because of our start. So that's why we keep the negative value here in particular. So remember, just to reiterate what I was explaining to you guys, this x of n signal here is going to be stationary for a convolution. But in doing the convolution, remember, we need to have a stationary signal and we need to have a sliding signal. So because it's convolving with itself, remember, that means we need to flip that x of n signal and then we need to slide this x of n signal accordingly. So because this here, x of n here is going to be stationary, and x of minus n here, when we transform this into n minus k, is going to be our sliding signal. The start point here being -5, we use this as our start reference to figure out, okay, what's going to be our starting index for y of n. And this here being at -5, we only need to focus on the magnitudes for our start points, and we're just going to factor in that negative sign later on. So the start point here for x of n is going to be at -5, but the start point here for the sliding signal of x of minus n or x of n minus k here is going to be 5. And we're going to focus only on the magnitudes here, so we're going to add the two together, which is 5 plus 5 is equal to 10. But for the stationary signal, the starting was negative, so we factor in that negative at that point. And as such, we get a result of the starting index here being at -10 in particular. Any particular questions as to how we got this -10? Or anything that needs to be cleared up? Okay, it looks like we're pretty much fine, so let's watch part 2 of that question. So the part 2 of the question is, what's the value of the first non-zero value in the convolution? So that's actually pretty simple at this point. So y of minus 10 being our start value here. We're just going to watch what were our starting values. So this here was 3, and this here was minus 4. So we just multiply the two together. Let me just make sure it was that. Oh, whoops, sorry. I said that wrong. Our start here was 3, and our start here for x of n was also 3. So that's just 3 by 3 here, which gives us a value of 9. So start x of n multiplied by start of x of minus n. That's 3 by 3, gives us a value of 9. Because the start here for x of minus n here was 3, and the start here for x of n was 3. So that's just 3 by 3 gives us a value of 9. That's pretty self-explanatory. Let's see for part 3 now. So what is the index of the last non-zero value in the convolution? Okay. So if we have the index for the last value of the convolution, that means we need to figure out how many overlaps that we're going to be encountering in particular. So we need to figure out what's going to be the length of our sequences here. And then we're going to use our start point and factor that in to figure out, okay, what's going to be our end point. So our sequence here goes from 14 to -5. And you may think, okay, we just add the two together so we get 19 samples. But no, that's actually wrong. And I'm going to explain why that's wrong. So let's actually watch this on a smaller scale, right? Let's say if we had an example sequence here going from -2 to +2, right? And you'll think it's 2 plus just the magnitude of 2 here equals to 4. Yeah, that's wrong. That isn't the length of the sequence. The reason for that being is that we have -1, 0, 1, and this length here is actually 5. So in calculating for the length of the sequence, so that means we have L here being our length is the start plus the end plus 1, because we need to factor in this 0 value here that we're going to be crossing. So we got 2 plus magnitude of 2 plus 1 equals to 5, which matches back up here. So always remember that, because you need to factor in that 0 value. That means you need to add 1 to those. So if we need to get the length of x of n here, we're going to call this L of x. It's going to be the start index plus the end index plus 1. I remember we're only taking the magnitudes of these indices. So the start index here for x of n was -5, so that's just going to be +5 when we take the magnitude. The end index here was 14. So magnitude of -5 plus 14 plus 1, which gives us a value of 20. So the length of x of n here is going to be 20 samples. Because we know it's 20 samples, that means the convolution while n is going to be L of x plus L of x minus 1. Because we need to figure out what's going to be the length of our convolution. So we're going to rewrite this as L of y here. That's going to be 20 plus 20 minus 1. Means that's going to be 39 values for our sample. Sorry, for L of y being y of n. We had that convolution equation from the previous question. Now, we also need to factor in our start point now to figure out what's going to be our endpoint. So the starting index here was at -10. And we know what's going to be the length of our convolution here being 39. So that means our end index of y of n is going to be L of y plus the start index of x of n. And well, typically we say it's going to be L of y minus the magnitude of the start index of x of n. That's going to be 39 here minus the magnitude of our start index of, sorry, not of x of n, sorry, my mistake. This is going to be the start index of y of n because we've calculated for the index of y of n. Sorry, that's my mistake there. So the start index of y of n, which we calculated just now from part 1, was -10. And we're just going to be taking the magnitude of this. Because it's calculated for the end index of y of n. So it comes like this, just going to be 39 minus 10. So we get the end index here being a value of 29. Any particular questions for part 3 here? It looks like everything is okay here. So the last part, which is just going to be part 4, that's also very self-explanatory. So this here is just going to be y of 29 that we're going to be trying to calculate for. And part 4 basically asks what's the value of the non-zero value in the convolution. So this here being, let's go all the way back to our visual representations. We're just going to be watching the value of the finish points here, or the end points, which is going to be -4 by -4. So this is going to be end of x of n multiplied by the end of x of minus n. It's going to be -4 multiplied by -4. Gives us a value of 16. So yes, that's very self-explanatory at that point. Alright, so The last question that we're supposed to be doing here, and I'm watching the time in particular, is question 7. So let's actually move on to that immediately. 7. And question 7 here was asking us to find the convolution of the following two finite sequences and confirm your answer using MATLAB. Okay. So I'm going to have to use MATLAB here a little bit, but I'm going to use Octave Online, which is similarly the same thing as MATLAB, for me to formulate my sequences here. Put this for Octave here. What's this? So for our first signal here, which is x of n, this is 0.5 of n, going from u of n to u of n minus 6. And that means n here will be going from 0 to 6 in particular when we watch this. So for my, I'm going to call this n1 here. I'm going to say n1 here is going from 0 to 6. So we get 0, 1, 2, 3, 4, 5, 6. And then I'm going to say x here is equal to 0.5 by n1. So this gives us our x vector, which is required. Now, reason for this why I'm saying n1 here went from 0 to 6. If we watch the unit step here, u of n and u of n minus 6. N here, if we watch the brackets, that's n equals 0. And if we say n minus 6 here is equal to 0, that means n is equal to 6. That means the difference of the unit steps here just means that n goes from 0 to positive 6. And that gives us the range of n here for x of n. Similarly, for h of n here, that means n here being n plus 3, the start point is, if we say n plus 3 is equal to 0, that's going to be n equals negative 3. So I'm going to call this n2 here. Goes to negative 3. And then we have n minus 4. So if we say n minus 4 here is equal to 0, that means the n point here is going to be n minus 4 equals 0. So that's n equals positive 4. So that means my n vector here for h of n goes from negative 3 to positive 4 by watching the unit step difference here. And then I need to get my values for h of n here. So we're going to call this h equal to 2 multiplied by sine of n2 by pi divided by 2. So I get my values here for my h vector. So let me bring back up my whiteboard here. For the time being. And put this here. So that means here that now I have my x vector being 0, 0.5, 1, 1.5, 2, 2.5, and then 3. Right. Back to it. And I also have my h vector here, which is 2, 0, minus 2, 0, 2, 0, minus 2, 0. Good. Just minimize this octave for the meantime. We can see here that both of these sequences that we just now calculated for 1, 2, 3, 4, 5, 6, 7, 1, 3, 4, 7, 8. So we're going to have a difference in lengths here for our sequence, and that's okay if we have an uneven convolution. It's perfectly fine. It just means that now we're going to be dealing with the convolution table in a different manner in particular. Is there one thing I might get to? No, that's perfectly fine. All right, okay, nice. So let's set up a convolution table, and I'm going to be drawing this here in particular. So as I said, it doesn't matter where you put the X signal or the H signal on the convolution table. The order of the convolution doesn't matter. 0, 0.5, 1, 5, 2, 2.5, and 3. Have 2, 0, minus 2, 0, two, 0, minus 2, 0. Draw the table accordingly. So anything that's going to be 0 here, multiplying inside this convolution table, that just means we're going to have zeros throughout the entire table. So this entire column here is just going to be 0. And these rows here are just going to be 0 as well. And then we can just multiply out each one of these here. So 2 by half will give us 1, 2. This will be 3. This will be 4, 5, and 6. Let's say it will be minus 1, minus 2, minus 3, minus 4, 5, and minus 6. Similarly, because values just keep on repeating, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Right. So we need to figure out what's going to be the output length of our convolution here, which we're going to call L of y. So that's L of x plus L of h minus 1. And L of x here was 0, 1, 2, 3, 4, 5, 6, 7. So that's 7 here. Plus L of h, which was 8 minus 1. That's 15. That means we're going to have 14 samples in particular. Now, we have our convolution table here, and I know it's going to be a little bit long if we have to like do all the summations for the anti-diagonals and so forth, because like I explained a little bit earlier, the anti-diagonals will start at these points here as we keep on going, that I'm circling in green. And that actually can be a little bit tedious for us to do. So what I'm going to show you guys here is that you can actually use MATLAB to get, or Octave online, get your output sequence instead of having to sum up all those anti-diagonals in particular. All you need to do to make sure is that when you multiply out the values in each one of these cells for the convolution table, you need to make sure that these values in the cells here are going to be correct, because these values in the cells here do count towards marks. So just make sure the values in the cells here are correct, and you don't need to bother about doing the summation for the anti-diagonals. Once you have the sequences here in Octave, I'm here for a little bit. Once you have the sequences here in Octave, there's a nice handy function that you can call here named conv, and we say x, h, and that gives us our convolution output. So that actually does the work for us to get the output required. So y of n here is just going to be 0, 1, 2, 2, 0, 1, 2, 2, 2, 3, 4, minus 3, minus 4, 2, 2, minus 5, minus 6, 0. And as we see here, columns 1 to 8 and 9 to 14, there are 14 values that matches up with our L of y. So what I would like for you guys to actually attempt, even though I'm showing you guys that you can use MATLAB to do this, you have the convolution table here. Come across the anti-diagonals, because I'm giving you the start points and you know it needs to go through each one of these cross points here in the table, and see if you can verify the answer for y of n here. And it's going to be the same answer, I promise you that, because we just not calculated that using the convolution function in MATLAB or Octave accordingly. And yeah, we're basically out of time at this point because I know I've gone over time by about 4 minutes. So I will post the solutions for problem set 1 online. There are some small errors. Yes, I know. If you do point out the errors, I'll fix them accordingly and I'll re-upload the solutions for you guys as well. In particular, I believe for question 6 that we just noted. What's question 6? Question 5. Question 5. Right, the solution for question 5 that is provided. One of these values here is wrong. The value that I did here live is correct. So if I spot it, I'll fix it on the solutions before I upload it. If I don't spot before then, if you do happen to see it, just point it out to me and I'll fix it on the solutions and re-upload them in particular. Yeah. So next week, our lectures are going to be focused on spectrum analysis. And that also is a little bit of an important topic as well. I will also upload problem set 2 if required, if we did complete all the material. If not, if you don't see it uploaded because we didn't complete all the material in time for problem set 2. So until next week, take care, be safe, and I'll see you guys soon. Oh, and if you have any questions to ask, feel free to leave them in the comments or email me directly. All right, so take care, be safe, and I'll see you guys next week. Later. I'm still there. So, in answering that question, you can just use MATLAB. You don't need to show all the additions of the diagonals. So what you can show is what I've done here is the start points for the anti-diagonals. So just visually draw those circles to show, okay, this is where you actually start doing the summations for the anti-diagonals, and just use MATLAB at that point and formulate your y of n. Alright, see you guys next week. Later.